Well, good morning. Welcome to our vacuum filtration technical session today. For those that don't know me, my name is Greg Vaughn, and I have two companies that specialize in vacuum and leak detection. Schoonover is over 50 years old, is my manufacturer's representative company. Apex Vacuum is my direct sell products company. Apex has their own products for vacuum and leak detection, but also partners with industry leading brands to provide my customers with the best product solutions to help keep production up and running. Today I have Mike DeLisi of Solberg here to talk vacuum filtration. The reason this came up was in visiting locations over the years, I've seen lots of applications had particulate and vapor issues that affected production and the vacuum pumps and led to premature failures. In working with Mike, I realized that if I didn't understand vacuum filtration very well, my customers might not either. So that led to this technical session. So Mike has probably a 30-minute presentation, and then we can take questions. So at this point, I'll let Mike take over from here. Welcome, Mike.
Good morning, everyone. How are you? I'm going to be sharing our presentation here shortly. Let me know if everybody can see it. All right. So like Greg said, my name is Mike DeLisi. I'm the Global Market Manager for Solberg, and we've been in business for about 52 years now, and our goal is to help protect vacuum pumps. We actually have three different sectors: vacuum technology, compressor technology, and power generation. So today we're going to jump right in and talk about protecting your vacuum pump. So our mission statement, which is very important to what Greg and I are doing here, is we partner with our customers, colleagues, and suppliers to help them innovate and discover new possibilities. The reason why this is important is because it's really up to our customers to tell us what they need, and we'll do everything we can to help them innovate new products. So this is really, strong and important for us, especially in today's climate. So as you can see, we have over 20 locations. We have our headquarters in Itasca, Illinois, where we manufacture all of our products. And we're going to talk about filtration today. So we'll jump right in. The objectives for today is to discuss the importance of filtration, what kind of contamination we can stop, what kind of information we need from you all to help properly size and select a filter. And then we want to talk about how do we protect the overall health of the pump, which is very important. And then last but not least, how do we protect our people, our employees, and our environment? So let's dive right in. What is the purpose of filtration? So basically, filtration is just to help stop any contamination from entering an area where you do not want it. So the first step of protecting would be on the intake side, let's just say on a compressor. So we want to stop any of the environment from entering the intake air. But today we want to focus on the equipment and the process and the environment. So we're going to focus on these two right here, which is protect the equipment from the process and then protect the environment from the equipment. And what that means is whatever your process is generating, whether it be particulate, liquid, or vapor, we want to make sure it doesn't enter the vacuum pump and hurt any of the inner workings. And then anything that does make its way into the pump, we want to make sure that it does not enter the environment, because we don't want to harm our workers and employees. We also don't want to, pollute the environment. So this is the basics principles of filtration and separation, and what we want to pay attention to in order to protect the equipment. So what kind of contamination can we remove? Well, the four basic contaminations that we want to take a look at are particulate, which is the most basic. That'll be your dust, your powders, anything that has thickness to it. The next, which is a little more tricky, is liquid, which could be a water or any type of viscous material that you'd be pumping on. And then even more difficult, which would be aerosols, which would be contamination that would be presenting as a smoke. And then the most challenging, which would be vapor, especially under vacuum. Vapor is very tricky to stop and contain inside of a housing. So we'll go through some of those requirements in order to stop vapors in a vacuum application. So what kind of information do we need to select the filter? These are the key concepts. So we're going to go through them, and we're not going to go too deep, but we're going to explain what we look for in order to size a filter properly. So we first select a vacuum pump. And when we select the vacuum pump, that pump is going to have a flow that we want to pay attention to. And it's not that important overall, but we want to know what the mass airflow volume that the pump is able to produce, because we don't want to interrupt that flow. So we always start with the flow of the pump, and then we start working down through the other requirements. When we start looking at the actual contamination and what the process is generating, we want to understand what the median micron value is. Now, maybe in a wood routing application, we know that dust or wood chunks would be maybe between 10 and even 1,000 micron. So we need to know what size the contamination is so we know how we want to stop it. And then we want to talk about efficiency. Depending on the pumping technology, we want to understand how much can that pump ingest. If it's a rotary vane pump, we want to try to keep all the particulate out of the oil. So for example, our 5 micron polyester media, which is a standard media that we use, this will have an efficiency rating of 99%, meaning anything larger than 5 micron, it's going to stop 99% of that contamination. So we want to make sure we're paying attention to efficiency. And then we're going to start talking about pressure differential across the filter element. And this is important because as we're building a vacuum system, we want to make sure that we're not interrupting the throughput of the system. And by putting a filter up or a wall, this is going to hurt the actual throughput of the system. So we want to make sure when we design and implement a filter that it's not going to hurt the performance of the pump. And I think most importantly, we want to understand what the vacuum level is in which the process is working. So if it's a rough vacuum application operating closer to, let's say, atmospheric conditions, well, then we know that there's going to be a high mass flow rate, which is going to allow us to have to size upward of the filter so it can accommodate not only the flow, but the contamination in which the process is going to generate. If it's a deeper vacuum application, then the molecules obviously slow a little bit. So then we don't have to worry about throughput as much, but we have to worry about conductance and making sure we're not interrupting those molecules while they're starting to transition from a turbulent flow over to molecular flow. And then last but not least, temperature is very important as well, especially if we start dealing with liquids or gases or vapors, because depending on the temperatures and the vapor pressures of the contamination will determine how we actually stop the contamination from migrating through the filter. So these are the key concepts that we want to pay attention to when we're sizing a filter, and what we're going to do to make sure that we're going to have the filter run efficiently and not affect the throughput of the system. So how do we protect the vacuum pump? Basically, when we start with particulate removal, it's the most easy way to stop contamination. So these are just some of our general products that we won't go into too much detail, but essentially our CSL and WL is just a standard particulate filter that would be like a one size fits all. You might see a lot of these filters on prepackaged vacuum pumps, and what the intention is just to stop any particulate from entering the system. But there's going to be situations where you want to see what the process is generating. Maybe you don't know exactly what the process is generating. So then we go through it to a see-through filter, which is really important to note. If you can see here to the left, there's a see-through bucket and then there's a filter. This bucket's going to allow you to see everything that the process is generating and make some changes on the fly. For example, if you started with a 5 micron filter element, perhaps it's too tight and it's getting clogged quickly. So you might want to move over to maybe a wire mesh or a coarse efficiency filter. So seeing the process is very important to most of our customer base so they can determine if the filter that they're using is being effective. Then we move down to our Spinmeister series, which is almost like a pre-filter. The goal of the Spinmeister, which is basically a fan, if you can imagine a fan spinning and knocking out wood routing dust or wood chips, what the intention of this filter is to stop large particulate from actually hitting the filter media. So it's prolonging the life of the media, which again, we want to protect the pump, and then we want to look at unique ways to help protect the filter element as well. Then there are going to be some significant challenges, maybe in vitamin manufacturing or just any process that generates a fine dust. And what we do is we move over to RST, or reverse pulse technology, which is very tight efficiency. So it's 0.3 micron at 99% efficient. So what that's going to do is it's going to stop any fine dust being generated, let's just say from a vitamin manufacturing standpoint, and it's going to pulse during the process to clean the filter for you. And the reason why it does that is when you have tight pores in a filter system, they can clog very easily. So we want to make sure those pores, just like the pores in your skin, we want to keep them unclogged, and we want to make sure that there's no interruption to throughput. So that technology helps keep the filter clean. And then we have our HV medical vacuum series, which in today's climate is very important. These filters are used for medical vacuum air, and it stops bacteria from moving towards the vacuum pump. And why that's important is because if any bacteria makes its way through the vacuum pump, when that pump has to be rebuilt, it's going to become a biohazard matter, and there's not going to be a lot of rebuild shops that are going to want to handle that pump during the rebuild phase. So this filter is designed to keep bacteria out of the system and out of the vacuum pump. And so this is just our basic way of removing particulate. Particulate is very simple because you can see it, you can quantify it, and we have very simple ways of keeping it out of the pump. But as it gets more difficult, we move over to liquid. Now, a lot of the liquid removal comes from applications like food processing, or any process where maybe you're working with chemicals or solvents and they're in a liquid state. Now, a lot of the times in a liquid state, it means that we're probably working at a rough to medium vacuum level. So we start to introduce technology like the STS or any of these other liquid knockout pots. And what the STS essentially does is it knocks out any liquid in the airstream. And there's a ball, which is very hard to see right now, but if there's a ball in here that will go up into the cage and deadhead the pump when it's full. So what this does is it allows no liquid to be ingested into the pump system. And there's going to be scenarios where there's going to be a lot more liquid that we have to worry about. So we migrate over to an LRS or an SRS. And what this technology does is it's a multi-stage knockout system that uses mechanical baffles. It uses a demister pad. It uses expansion ports and a polishing filter to make sure all the liquid is knocked out. And a lot of the times in chemical processing, you need a multi-stage approach in order to knock out the liquid. And then obviously once you contain the liquid within the housing, you then have to drain it. So there's drain packages available that can help drain under vacuum and not interrupt the process. So liquid would be the second most difficult thing to stop in a vacuum system. And it actually is the most harmful to a vacuum pump, because if you ingest liquid into a vacuum pump, you're essentially drowning it and it won't be able to move the volume of air that it's intending. So it's important to put something in front of the pump to knock out any of the liquid that it may see. And as we move on to the most challenging, which is vapor, we look at these two different technologies here. So one's a smaller technology with see-through visibility, and then one's a really large system. So we have the JST and the JRS. Now, the reason why vapor condensing is very difficult is because many factors come into play here. So we have to look at temperature, vacuum level. We have to look at residence time, which is basically the time in which the contamination is going to be seeing inside of this cold housing. And then we look at flow dynamics, and then we look at vapor pressures of the actual contamination. So unlike the particulate filter, particulate we can see and feel and we understand how to quantify it. Vapor is very difficult to quantify. So when we're designing a system that needs a vapor condenser, we require a lot of information up front. So we want to know what kind of vacuum system you have, what kind of vacuum pump you're using, if you have any other condensing products that are in place. And then from there, we run extensive calculations to make sure we have enough surface area, we have enough cooling, and then we have enough other basic like baffles and expansion chambers to make sure that we're actually knocking out the vapor. So these are very intense applications and they require a lot of thought. So when we go back to the particulate, very simple. We can see the dust, the liquid. We can see that there is obviously a high volume of liquid being pulled across with the vacuum, and then vapor, very difficult, but can be stopped, taking the right steps. So the next chain of events would be, maybe you don't have a budget for the vapor condensers. Maybe you don't have the footprint, or maybe you already have a filter in place that's stopping particulate and the process has changed. So what we do is we might migrate over to a adsorptive media. Now what we would do, if you can see the see-through housing here, just like we talked about with particulate, we would take out that 5-micron media and we would put in a chemical cartridge. Now the chemical cartridge needs to be compatible with what the process is generating. So let's just say your process is generating a lot of oil vapor. Oil vapor to me tells me that we could use an activated carbon media. We would put it inside of that filter housing and it would absorb instead of condense or knock out any of the oil vapor that the filter is seeing. And then as the processes get more intense, perhaps you're pumping on hydrochloric acid, or maybe you're in a research facility with a lot of different contamination that you're worried about stopping. We might move over to an activated alumina adsorptive cartridge. And what this allows is to neutralize any of the acids, and it's going to absorb any of the hydrocarbons or any of the moisture that the process is creating. So basically, this is the last chain of events when we go through a vapor or a liquid separation application. Is okay, we've knocked out the large particulate, we've knocked out the large liquid, and now we need to absorb the vapor. So this is the kind of technology we would deploy to protect the overall health of the vacuum pump and make sure it doesn't ingest any of these chemicals. And most importantly, how do we protect the environment? So we know that the pump is going to ingest some sort of contamination. Early on, we talked about efficiency, and we talked about how at 99% efficient, that's how the pump is going to see contamination. That means 1% of the contamination is going to make its way through the pump. Well, we want to help stop that contamination from exiting the pump and into our environment. And that's why one of our mantras is protecting your equipment and protecting your environment. We have to do both. So then we look at how do we protect the exhaust side of the vacuum pump. And it's very simple. On a rotary vane pump, for example, it generates an oil mist. So we would use just a basic HDL or an oil mist eliminator that would make sure no oil mist comes into the environment while you're pumping. Now, anyone on this call familiar with vacuum pumps, if you've ever had the pump just pumping on air, just meaning wide open or a very large volume, you'll see oil mist escape the exhaust of the vacuum pump. So when you install one of these filters on that exhaust, it will knock out all of the oil and any contamination that the pump may have ingested. But there's going to be some situations that maybe the pump was pulling on something that had an offensive odor. Perhaps it had some sort of chemical associated with a vapor that was processed, and as the pump ingested that vapor, it's going to want to discharge it through the oil mist. So then we move over to dual stage filtration, which would be the same coalescing media that would stop the oil mist, but then we introduce an activated carbon element to get rid of all of the odor and any chemicals that may have been ingested by the pump. So now we know that whatever environment we're in, if we're in a lab or we're in a building or we're in a dentist office, we know that this oil mist and the odor that the process is generating is not going to enter that environment. And that's basically it.